Hello, my name is Pavel Malishkin. I'm from Ekhe Tusayuhin in Estonia, and my presentation will be about the combinatorial approach to machine learning and new application opportunities that may arise from that. This is a new approach, and I am also going to make a short demonstration of the proof of concept to maybe inspire your thinking in this direction. The motivation of this work is that humans somehow are able to combine models they learn from different scopes. And as long as machines lack this capability, humans will have to design models for the machines because humans are able to do that, and the machines are only able to adjust these models, or maybe prove these models statistically, or maybe derive some computational results from these models, but they will never invent anything new on this way. Maybe you are familiar with an opinion shared by a number of experts in artificial intelligence that 3-year-old kids are still much more intelligent than the best computer learning systems, because the kids are very inventive and very creative, while the computers are not. And this is also the reason why computers can't repeat what humans do in engineering, design, and programming. On the first glance, human's brain is able to produce something new just from nothing, like on the left. While in most of experiments in machine learning, the machines have some ready model from the beginning, and they only need to adjust it, like on the right. Most of the machine learning experiments may be considered as just optimizations by a number of criteria for a model of a fixed structure. But there are some attempts dedicated to structural optimization of the models, and you may think of our combinatorial approach as of another technique of structural optimization. But it seems to us like being a bit closer to a human's thinking method. The main idea of the combinatorial approach is that humans propose new hypotheses as combinations of models they have learned and proven before. For instance, walking skill is a combination of a number of other skills, as it combines the knowledge of how to keep the body upright and the knowledge of how to move the limbs, and staying upright in its turn is a combination of the skills of balancing and body straightening, and all these skills need proper managing for a number of muscles, so each one of them is another combination of simple skills. And you can note that each of these skills can be used not in just one combination, but in many combinations for solving various problems. So one thing is to train a model, and another thing is to learn how this model can be used in combination with other models. And this second thing is very important for learning as well. Humans used to combine models for solving everyday problems, and we are all familiar with the concept of research, which is a repeating search for models and ways how to combine them. We can think of this activity as of a combinatorial function which is implemented in the algorithm of humans thinking, but not yet in machines. Well, this combinatorial function is based on some prior assumption that should be introduced to the artificial learning agent to make it more effective. And this can be effective only if the application domain is structured, meaning that the big model of the scope can be combined from simpler models that can be used individually or in combinations with other models. But this is the case in many applications, if not to say in all of them. We know that systems consist of smaller elements, and processes use results of sub-processes, and materials consist of simpler substances, and human languages and science systems are also structured. Human models that reflect the properties of the real world are structured, so there is little difference between comprehending a model and learning a real subject from this point of view. And we find everywhere that a more complex model is combined from simpler models. This means that a combinatorial function, when implemented in a machine algorithm, will be effective in almost everywhere, from research and development of real things and processes to communicating to humans on how to use models. And though the concept of combinatorial functions seems obvious to any one of us, it looks like not only encouraging results in this problem are absent, but the research itself is not going. This is why we focused on this problem some while ago. And now let me finish with the introduction and switch to the main part of the presentation, where we shall get acquainted with a combinatorial agent, which is a proof of concept for the artificial combinatorial function. And we shall also see some demonstration of its abilities in learning to some simple problems and write programs that also solve these problems. And these results were first achieved in November 2018. So let's consider an environment where an agent interacts with an infinite board where a piece is placed. The agent gets states from the environment and rewards for its activity, and is able to perform some actions, and all this looks like usual for now. There is also an execution unit in the environment the agent can program. What the agent is expected to learn? It has to learn how to move the piece on the board. It has to learn that there is some useful information in the messages that come from the environment. It has to learn a relation between numbers it uses itself and their designations in messages that come from the environment. It has to learn some simple programming language and start using it for writing useful programs for the execution unit. And finally, it has to launch the program it has written before. Now I shall spend some time to explain these aims in some details. First, the agent deals with a piece that is placed on an infinite board. To move the piece, the agent has to take it, shift the hand in vertical and lateral directions, and put it into the new position. There are board rules that define how the piece can move laterally and vertically, and though the agent always needs to take the piece and put it back, the agent needs to learn that there are rules and move the piece accordingly. The board rules change regularly, and the environment informs the agent about that by sending a pair of symbols. The agent has to derive the meaning of such messages. Well, then you know that there are numbers and their designations, and the relation between them is something that everybody learns when being a kid. The same is about the agent, as the messages it receives use some designations, and the agent itself uses something like numbers to make a move. So it needs to build a kind of relation here. And there is an execution unit in the environment that can be programmed. The programming language is very simple, as it contains only two keywords like begin symbol to start a program and end symbol to finish, and any symbols that the agent might need to move the piece can be used in the program body between the begin and end. So the language doesn't provide any loops or conditional operators. It is very simple and not Turing complete, obviously, but still it's a programming language that the agent can learn separately from any other models. The next thing is to program some useful functions. In our case, this means that functions able to move the piece. As there are no conditional and loop operators in the language, the agent has to rewrite the program each time the board rules change. And finally, the agent has to learn how to launch the program it has written. This is also very simple, as there is just one special symbol for that, but still the meaning of this symbol needs to be learned by the agent. There is a reward system from the environment to the agent, so there goes a kind of reinforcement learning. If there were rewards only in case of writing and launching a useful program, this might be a sparse reward system, and the rewards might be very rare. So it's practical to split the total reward into smaller rewards for simpler agent section patterns, where the full reward is made only when the final goal is achieved. That is the goal of writing and launching a useful program. So in the experiment, the agent gets rewards when it moves the piece itself, as if by its hands, taking and putting it into a new position, for writing the shortest program having an effect of moving the piece according to the current board rules, for sending a correct pair of numbers after receiving a pair of number designations from the environment, for launching a previously written program, for sending a correct number after receiving a number designation from the environment, and for any syntactically correct program, that is, any sequence of symbols within the brackets begin and end. The whole experiment is divided into 4 stages. The reward system changes as the training goes on, and there are a number of reasons for that. First is that some rewards are simply not attainable on each stage because some situations may not allow the full reward. And another reason to add rewards step by step is to manage the training process and also make the training results more clear for understanding. On the first stage, the agent learns only relation between numbers and their designations. So the environment sends just one number designation, and the agent has to reply with the corresponding number. Then the agent is trained to reply with the correct pair of numbers on a question containing 2 number designations. On the third stage, the agent learns how to move the piece, and finally on the fourth stage, how to write a useful program that moves the piece. So you see that we follow the training rule from easy to hard. We train simpler models first, and then train how the models can be combined to get models that are more complex. And this is very similar to how humans learning goes. On the first stage, the agent learns only how to reply with a number to a question with one number designation. So one can say it inputs and outputs one tuples. On the second stage, the agent gets a reward when it outputs 2 tuple for a 2 tuple in the input. It can also get a reward for a tuple of any length if it contains correct pair of begin and brackets, as this is a program, or a reward for launching a previously written program. And this concept cannot be even described by a tuple of a fixed length correctly. The third stage is about moving the piece, and the agent has to produce a 4 tuple for the same 2 tuple input to get a better reward than before. And finally, on the fourth stage, the agent produces a 6 tuple of program for a 2 tuple input. Thus you can see that the combinatorial agent doesn't need to have prior knowledge of the length of the tuples it deals with, so the structure of its inputs and outputs is not fixed, and it is not fixed priorly where the input vector starts and where it ends. The input is given just as a flow of symbols, and the agent itself is defining the margins of the messages. The agent also doesn't know when a transfer from one stage to another takes place. It can only guess that. We shall start our demonstration now to see how it works in real time. So we have a kind of board here, and this is a piece that will jump when the agent moves it either manually or by launching the right program on the execution unit, and we shall see if the move is made manually or by the execution unit. And we have a total number of moves here, and we shall also be able to follow the progress of the agent here. The training scheme will allow the agent getting on the next stage only when its behavior patterns on the previous stage is confident enough that it has learned everything right. This is a log of all communications between the agent and the environment. Agent phrases are on the left, while those of the environment are on the right. The rewards to the agent are marked by pluses. You see that the agent is not limited to any size of its phrase. It has no prior knowledge on that. And now the input for the agent contains only one symbol, and it will contain 2 symbols on the next stages. Well, we also have a number of performance indicators in our training panel. Here they are. We show frequency of proper usages of numbers and frequency of proper usages of pairs of numbers according to the current board rules, and frequency of moving the piece on the board either manually or by the execution unit, and frequency of writing syntactically varied programs, and frequency of launching a program written before, and frequency of launching the shortest possible program that moves the piece. Actually, these indicators just show the frequency of which kind of reward the agent earns when training. Okay, let's see what has happened here while we were discussing the indicators. We are now on the second stage, and we see the moment of agent's understanding of the relation between the number designation in the input and numbers expected in the output. And now it started using this relation in the second stage. The agent doesn't know how to write programs yet and how to move. Though it can try to move the piece already, it just doesn't get rewards for that, so it does not do that regularly. So let's wait a couple of minutes more, and in the while I'd say that the agent is now running on a single core of 1.6 MHz CPU, and no other means of acceleration are used. And now you see this process is using only 6 megabytes of random access memory, and it will use not much more when the training is complete. Now we are on the third stage, and you see that the agent has made some moves already, and it continues moving the piece manually. And it also has been writing and launching programs, and we can see them here. These are the programs it writes, and we can expect that soon the agent will come to an idea that the moving skill can be combined with the programming skill, and the first useful program will appear in this moment. You can also mention that the agent does not stick into a local maximum of the reward function. It tries to find new combinations of its models, and thus it will probably not stick forever in a local maximum. We can see some declines in the indicators here. That may be the signs that the agent continues looking for more models, as if it's not satisfied with the rewards it has already. You see now that the agent has written a number of useful programs here, and you can see their code. The yellow flashes on the left of the board monitor show that it also launches these programs successfully. And finally, the fourth stage is complete, and congratulations. Okay, let's check the characteristics of the machine again, and certainly we can work faster if we use GPUs and involve more computational methods and resources in our approach to get more impressive results. But what we can see already now is that the combinatorial approach is relatively simple to compute. And to summarize, I would say that the combinatorial approach is working, and the agent learns from easy problems to harder ones, as it combines simple models to more complex. And this is an effect that is promising to exclude the artificial intelligence expert, which is now needed to define the structure of the learning system, from the development in the future, as the system itself will be able to learn simple models and combine them into more complex models. And we think that the combinatorial approach is much closer to how humans learn and train each other, and we hope to impress you with more results soon. The aim of this research is to make an artificial agent that is able to learn like humans, and in this meaning able to research like humans. And we hope to have an agent that is able to exchange results of its findings with humans and communicate with humans to study models. The next step is to train the agent to program on a language that is Turing complete. And this kind of agent might be considered as a useful prototype, as it could be used in programming applications with minor changes. In the prospect, the agent could be used in applications related to design, engineering, and programming in a scheme that is significantly different from the state-of-the-art approaches where, for example, any programming framework gets the input not in terms of requirements to the solution, but in terms of structure or parameters of the solution. So the user needs to go deep into the details of the solution architecture and processes. With the use of the combinatorial approach, the user might train the agent some language to set requirements to the system, and this could be some extension of XML, for instance, and the agent might deliver a ready solution in a formalized language, like a Turing-complete language in case of programming. And I also have to say that we are looking for an application-oriented partner now, to start training the agent to do something useful. In this cooperation, our role might be training the agent's common sense like physics, mathematics and system analysis, as well as languages and science systems, while the partner's role might be in the supervision of training in the application domain. Many thanks for watching, and you may contact us if you have any questions or proposals. These were Pavel Malishkin from Egghead Osayuhin in Tallinn, Estonia, and the combinatorial agent is going to become a useful prototype soon. Goodbye.